This is lesson 33 in our Calculus 3 series, representing functions as power series. In the last lesson, we saw how series of this form can be recognized as geometric series, and therefore for absolute value of x less than 1, we know that this series will converge to 1 over 1 minus x. So we can say that for f of x equals 1 over 1 minus x, f has this power series representation for absolute value of x less than 1. And we wonder what other functions can be expressed as power series. Well, sticking with the geometric series form, we know that any function of the form a over 1 minus r, or we could call this r of x, would represent the sum of a geometric series of the form a times r of x to the n, for absolute value of r of x less than 1. So for example, if we have a function f of x equals 2 over 1 plus x to the fourth, we can write this in the form a over 1 minus r of x, and we see our r of x is negative x to the fourth, and our a is equal to 2. And this can be recognized as the sum of the geometric series 2 times negative x to the fourth to the n power. Now we should do a little bit of simplification on this because this is kind of an odd way to write our series. So we want to pull out the negative 1 to the nth power, and we have then x to the 4n. So this series looks like 2 minus 2x to the fourth plus 2x to the eighth, etc. And we know that this series will converge for absolute value of r less than 1. So that's absolute value of negative x to the fourth less than 1. And this reduces to absolute value of x less than 1. And this is our interval of convergence for this geometric series. Let's take a look at another example. F of x equals 1 over 4 plus x squared. Remember, the form that we're looking for is a over 1 minus r of x. So because we have this 4 here, we need to get that to be a 1. So the first thing we're going to do is factor out a 4 from the denominator, and then recognize that dividing by 4 is the same as multiplying by 1/4, so we could actually bring that 4 up to the numerator and make that numerator a 1/4. And so we can consider a to be 1/4 here. And then write this plus again as a minus negative. So we have our r of x is negative x squared over 4. And so here we have the series a times r of x to the nth power. And again, doing a little simplification, we pull out the negative 1 to the nth power. We have x to the 2n over 4 to the n. And we're almost done there, except we recognize that we have a 1/4, and we're dividing by 4 to the n, so actually we can combine these two denominators and make this 4 to the n plus 1 power. And so our series looks like this. And this converges for absolute value of r less than 1. And simplifying here, that negative doesn't have an effect because we're inside absolute value. We can multiply both sides by 4, and we have absolute value of x squared less than 4. And that gives us x squared less than 4, x between negative 2 and 2, or absolute value of x less than 2. This is our interval of convergence here. So we can say that for these x values, the function 1 over 4 plus x squared can be represented by this power series. We can get more functions with power series representations by using the following theorem. If the power series a sub n x minus c to the n has radius of convergence r that is greater than 0, in other words, it's not equal to 0, and it is possibly infinite, then the function f of x defined by this power series is differentiable on the interval c minus r, c plus r, and the derivative of this series is the series of the derivative of its terms. So term by term here, we can take the derivative. Derivative of a naught is 0. Derivative of a1 times x minus c is just going to be a1. So you have your a1 here. This power of 2 comes down. You get 2a2 x minus c to the first. 2a2 x minus c to the first. The next term here has a 3 that comes down. We get 3a3 x minus c squared, and so on. So this theorem is saying that the derivative of this series is the series of the derivative of these terms. So we're saying the derivative of the series is the series of the derivative of the terms. Now I want to point out that while this seems intuitive, this is not a trivial statement. Because remember that when you take a derivative, you're taking a limit. And when we sum up an infinite series, we're taking a limit of partial sums. So what this theorem is saying is that we could switch the order of the limits and get the same answer. And that's not a trivial statement. Here's an example where if we switch the order of the limits, we get a different answer. Here we have limit m goes to infinity, limit n goes to infinity, 1 over n to the 1 over m power. Now in this order, we're taking the inside limit first. As n goes to infinity, 1 over n goes to 0. So for each fixed m value, we have 0 to the 1 over m, which is just 0 for each fixed m value. And then you take m to infinity, well this is just a whole sequence of zeros, so that limit is equal to 0. But if we switch the order of the limits, first taking the limit on m, then taking the limit on n, we get a different answer. As m goes to infinity, we have a 0 in the exponent. That says for every fixed n value, we're looking at 1 over n to the 0 power. Well, that's going to be 1 for any fixed n value. Then we're taking the limit as n goes to infinity of a sequence of 1s. That's just going to be 1. So here we have two different values by switching the order of the limits. So this theorem, which says you can switch the order of the limits here and get the same answer, is a strong statement. And part 2 of this theorem is saying that the antiderivative of the series is the series of the antiderivative of each term. So the antiderivative of the series can be found by taking the antiderivative of each of the terms. And notice we have one constant c representing all of the constants that we would get from each of these antiderivatives. And again, this is not a trivial statement. And now for the interval of convergence of the series of derivative terms or the series of antiderivative terms, we know that the center of the series remains the same and the radius of convergence remains the same, but the behavior on the endpoints of the interval can change when you're looking at the derivative series or the antiderivative series. So the endpoints need to be checked whenever you're doing these computations. Now for the series that we were looking at above, summation x to the n, which converges to 1 over 1 minus x for absolute x less than 1, let's take a look at the derivative of this series and the antiderivative of this series. So first let's take a look at the derivative of this series. Now we know that that should be the derivative of 1 over 1 minus x, and that's 1 over 1 minus x squared. Now if we take that derivative term by term, we're going to get series n x to the n minus 1. And notice that we're taking n going from 1 to infinity now, because if we had n starting at 0, we're just going to get a 0 for the very first term. So why bother including that? We might as well just change our index to start at 1. So what we have here given by the theorem is that this series converges to this function. Now we know that the center of the series is the same, which is 0 here, and the radius of convergence is going to be the same, which is going to be 1, but we have to check the endpoints to see if when we took the derivative here, the behavior at the endpoints changed. So far we have convergence for x between -1 and 1, but we want to check the endpoints. Now, just by looking at the function to which this converges, we realize that x equal 1 can't be included because 1 over 1 minus 1 squared does not exist. But we can check it anyway in the series form and show that it doesn't converge. When x is equal to 1, we have a 1 here. So we have n times 1 to the n minus 1. This is just 1. So this is the series of n, as n goes from 1 to infinity. So, of course, that diverges. And when x is equal to negative 1, we get negative 1 to the n minus 1 multiplied by n. Again, these terms do not go to 0, so this sum also diverges. So in fact, our interval of convergence has not changed. It's still absolute x less than 1. You can write it in any of these ways. So we know that 1 over 1 minus x quantity squared can be represented by this power series for these x values. Now let's take a look at the antiderivative. We know that if we take the antiderivative of the series, we should be getting the antiderivative of 1 over 1 minus x. And if we use a u substitution to take this integral, we find that we have negative ln of 1 minus x plus a constant. Now the theorem says that we can integrate term by term here for this infinite series. And when we do that, we collect our constants, and we get summation x to the n plus 1 over n plus 1. So that tells us negative ln of 1 minus x plus constant 2 is equal to constant 1 plus this series. So if we solve for the function ln of 1 minus x, we can call this c, and we have ln of 1 minus x is equal to c minus the series x to the n plus 1 over n plus 1. Again, we know that this is true at least for the x values where absolute x is strictly less than 1, but we need to check the endpoints of this interval, so we have to check x equals plus or minus 1. And again, when we look at x equals 1, we realize that ln of 0 does not exist, so x equals 1 can definitely not be in our interval of convergence. But we can check by looking at the series. That would give us, for x equals 1, we get 1 to the n plus 1 over n plus 1, which is 1 over n plus 1. Starting at 0, this is exactly the harmonic series, and this diverges. For x equals negative 1, we have the alternating harmonic series, and by the alternating series test, this converges. So for this series, our interval of convergence includes x equals negative 1. And we're almost done, but notice we still have this constant hanging around. We need to figure out what this c is equal to for this function. And the easiest way to do that is by plugging in the center of the series here. So in our case, that's going to be x equals 0, or x equals little c in general. So here we take a look at our series, ln of 1 minus x is equal to c minus, and here we have x plus x squared over 2 plus x to the third over 3, and so on. Notice that when we plug in x equals 0, all of these terms are 0. So we get ln of 1 is equal to c, or 0 is equal to c. And ln of 1 minus x is just equal to negative of this series. So we have negative series of x to the n plus 1 over n plus 1, and going from 0 to infinity. Now let's take a look at another example. We know that 1 over 1 plus x squared can be recognized as an a over 1 minus r, and so we see this as the sum of the geometric series negative x squared to the nth power, which we simplify as negative 1 to the n x to the 2n. And the interval of convergence here is for when r, our negative x squared in absolute value, is less than 1, which is for absolute value of x less than 1. Now by the theorem, we can take the antiderivative of this function, and its power series representation will be the series of antiderivatives that we get here. So arctan of x we know is the antiderivative of 1 over 1 plus x squared. And so its series is going to be the series of antiderivatives of each of these terms. So we're going to add 1 to the x power and divide by that number, and collect our constants on the outside. So we've got arctan of x is equal to c plus the series negative 1 to the n, x to the 2m plus 1 over 2m plus 1. And we know this is true at least for the interval of convergence of the original series, which was absolute x less than 1. But we do want to check the endpoints here to see if the behavior has changed with the integration. For x equals 1, we take a look at the series, and we have 1 to the 2m plus 1 here, which is just 1. So we have negative 1 to the n over 2m plus 1. This is going to converge like the alternating harmonic series, and you can use the alternating series test to prove that. And when x is equal to negative 1, notice we get negative 1 to the 2n plus 1. Well, the power 2m plus 1 is always odd. So negative 1 to the 2m plus 1 is always just going to be negative 1, which means our numerator in total is going to be negative 1 to the n plus 1. And then we have a denominator still of 2m plus 1. So again, this is similar to the alternating harmonic, which is going to converge. So we want to include now x equals negative 1 and x equals 1 in our interval of convergence. So far we have arctan of x to be a constant plus this series for these x values, and we need to find our constant of integration. So we take a look at our series. We realize that when n is equal to 0, the first term we get here is x, and then we get higher powers of x after that. So when we plug in our x equals 0, which is the center of our series, we get arctan of 0 on the left side, and on the right side we just get c. Arctan of 0 is 0, so c is equal to 0, and arctan of x is equal to the series negative 1 to the n, x to the 2m plus 1 over 2m plus 1. Again, this is for x values between negative 1 and 1, including both endpoints. Now let's take a look at another example. Let's find a power series representation for f of x equals x arctan x. Well, we know that arctan x has this power series representation for these x values. We just found that. So x times arctan x is x times this series. So that means term by term, we have an extra power of x when we multiply this through. So this becomes x to the 2m plus 2 when we multiply this x in to each term. And so we have negative 1 to the n, x to the 2m plus 2 over 2m plus 1. And it's going to have the same interval of convergence. The behavior is not going to change at the endpoints by just multiplying a factor of x. And one more example, let's find a power series representation for arctan of x over x. So similar to what we did in the last one, we're going to start with the series for arctan x and its interval of convergence. Then arctan x over x is just 1 over x times this series. So when we bring that in, we're subtracting 1 power here. So we get x to the 2n over 2n plus 1. Now we need to be careful here. We said that our interval of convergence for this series is x going from negative 1 to 1, including both endpoints. So this series is also going to converge for the same x values. But notice that by dividing by x, we removed x equals 0 from the domain of our function. So when we say that this function can be represented by this power series, we have to remember to remove x equals 0 from the set of x values for which we say this is true. So even though the interval of convergence of this series includes 0, we can't say that this function is equal to this series for x values between negative 1 and 1. We have to omit 0 from that interval. So we would express that domain like this. So we learned in this lesson that functions of the form a over 1 minus r of x can be expressed by a power series representation by using the geometric series form. We then also learned that we could differentiate and integrate those functions and still get power series representations. And that's as far as we went so far, but in the next lesson we're going to see an even bigger class of functions that can be represented as power series. And this concludes this lesson on representing functions as power series.